Hello everyone, this is Leslie Pelch at the Vermont Center for Geographic Information, and I want to welcome you to our webinar today, Remote Sensing of Lakes, They're Not All Just Blue, with Shane Bratt from UNH Cooperative Extension. We're going to start out today with a brief overview of using the GoToWebinar interface, and then I'll hand things over to Shane. Let's see if my slideshow will open up. There we go. So the main things that I want to point out are the fact that you can open and close that GoToWebinar panel that you'll be seeing probably on the right or left side of your screen by clicking on the little orange button with an arrow in it. So if it for some reason is staying open and blocking your view, just click on that to collapse it down, and then you can always get it back open again by clicking on that same little button. If you are having any issues with your audio, then you can't hear me, but I'm hoping that you'll notice that there is an audio panel in your GoToWebinar panel, and you just click on a plus sign to open that up, and hopefully you'll see the correct information for calling in and also setting whether you're using your telephone or a mic and speakers on your computer. So make sure to get that all set right if you're having any issues. If you have questions that you would like to submit, everyone is muted other than Shane and I, and so you can submit your questions via typing them in to the question box via text, and those will come to me, so don't worry about sending those in at any time when the question occurs to you. They won't interrupt Shane, and if it's a question that does need to be addressed right away before he moves on, I'll interrupt him, and if it's something that we can save until the end, we'll probably save it till the end. Yes, and I want to mention the fact that the webinar is being recorded, and it will be posted at VCGI's YouTube page. And actually, now that I think of it, Shane will probably let you know that it will also be posted or linked to from the Cooperative Extension pages. I think he'll mention that. So the one other thing I want to ask everyone to do so that I can reassure myself that you can hear me is to click on this little button that looks like an orange hand with a green arrow on it. That's your way of raising your hand, and it just lets me know that you can hear me. Most of you are obeying. Not everybody, but okay. Thank you very much. And if you do have any questions, you can send me an email. I think my email is in the chat box. There's a little message in the chat box, and I will try to remember to check those to see if anybody's having any problems. I think that's it. Maybe I'll very briefly go to, oh, see, this is the thing I can't do is get out of my, there we go. Just want to head over to, so here's the VCGI website, and I just want to point out that this is right on the front page, vcgi.vermont.gov, and there's a link to our YouTube page right here. Okay, so that's it. Are you all set, Shane?
Yep, sure.
All right, I'm going to pass it over to you.
Just let me know when you see my screen and I can go.
Yep.
Show screen.
And I see your screen. I see remote sensing of lakes. They're not all just blue.
Okay, so let me just collapse the control panel. Okay. Well, thanks everyone for joining us today. As you can tell by the title, we're going to be talking about the remote sensing of lakes. As you can see on the bottom, I have two sort of different identities here at the university. So I am an extension specialist in geospatial technologies. I work through UNH Cooperative Extension, and my job is to try to figure out what types of geospatial technologies can be used by people in New Hampshire and break them down and try to offer training or information that lets people make decisions about what they could or should use. And then the other side, which probably most people in this audience don't know about, I also have recently completed my dissertation, and I am a professor in the Biological Sciences Department affiliate. And one of the main research topics I have is the remote sensing of lakes. So this is a little bit from a research side and also a little bit from what could the potential be, and what do you have to think about? What are the keys to think about when you might apply remote sensing of lakes? Now, there's a lot of information that we could talk about. I've given lots of presentations on this over the years, but what I've decided to do is try to give an overview in the beginning, some things to think about, and then some specifics of the latest research on lakes in New England. And then one of the things I was talking with Leslie about right before the webinar is that we could certainly do this again or be more specific or focus more on specific topics. So there'll be chances both either in comments from questions or also even at feedback at the end where you can give information about topics or sections of this that you'd like to see more on. So I'll get started here. And the title is funny that one of the things I think with remote sensing is that people see maps and as possibly GIS users, it looks like most of you are GIS users based on the registrations. People have a lot of confidence in maps if it looks official and it's printed or it's digital. But I think all of the times that you have maps, especially if you're doing any sort of translation where you're taking an image and turning it into a map of chlorophyll or impervious surface or land cover or cyanobacteria, for example, you really have to ask yourself, is that true? How accurate are these things? And it's very easy to create an image or that you can use in a map. But it really is important if you're going to use some sort of remote sensing approach or any analytical approach and make decisions on it, based on it, that you have an understanding of how well it works. And that would be my one point of caution, and something I've spent a lot of time working on is how do we know when we translate the remote sensed data to a map of something that we're interested in, that that map is something that we can use, something we can rely on. And so a lot of the background that probably most people have if they are a GIS user or have studied remote sensing is from land-based remote sensing. And a lot of times we all start out by doing land cover classification. So you have your image, whether it's Landsat or otherwise. There's a variety of bands you can use, and your ultimate goal is to turn it into something that looks like this. So something that has classes where it has urban and open and different sorts of forests and wetlands. And I took a class here at UNH where that was the exact thing that we focused on. And one of the things that was interesting to me as somebody who studies lakes and was interested in lakes for my dissertation was that one of the things that they said were the easiest to do was figure out which part was surface water or lakes. Now sometimes there's issues with shadows, but generally speaking, it's pretty easy to tell what lakes were. And really the conversation went something like this. First of all, look at the areas of this image that have almost no signal. There's almost no light coming back from it. And we can just color those blue because those are water. And since we're looking at land cover, we don't really care about water. There's almost no signal coming back. And now let's go on to the interesting stuff. Let's look at forests and wetlands and all of the cool stuff, and we'll leave that boring water stuff just colored blue and not think about it anymore. So obviously this was a little disconcerting to me, but it really is based on, number one, what people are interested in, and number two, the reality of what sort of signal comes back from land when you're looking at it from a remote sensing perspective. And we haven't talked about this very much. We'll talk a little bit more about reflectance and what it looks like. And you don't really need to know much about reflectance to understand that this shows a graph where there's a lot of activity. There's a lot of signal over different colors of light, different wavelengths. The water effect is down here. So if you have vegetation, you have different types of forests, different types of forest health, all of that activity is being seen in this dynamic range. The water stuff is all down here. So really, instead of working in most images, for example, with a signal that has this much dynamic range, you're really sort of stuck working with this little tiny part, which is why normally it's so easy to dismiss water as just blue and not having a lot of signal. But if you really care about the water, you do have some variability there you can look at. The question is, do you have the technology and the knowledge to be able to make sense out of and make sense out of the information that's there and also use it in an effective way? So the fortunate thing is that really all lakes are not just blue. There's a wide variety of colors of lakes, and obviously if we're going to use remote sensing, especially optical remote sensing with wavelengths that we can see, which is generally the most useful for water, it's pretty obvious that there are some differences. Again, the question is how do you measure them? And if you're using normal sort of limnological water quality sampling methods, usually you're interested in water clarity, chlorophyll, which gives you a decent amount of idea about productivity, and then perhaps total phosphorus, which looks at the amount of nutrients in the system. So really, how do you bridge these two ideas. How do you bridge the optical characteristics of water, what it looks like, to the actual information that you're interested in? And most people, when they look at remote sensing of lakes, they're really keen on the phytoplankton, the algae. They're keen on chlorophyll, looking at productivity. So the top example here, you can see looks very green. You would imagine that there's lots of stuff growing in this lake. The chlorophyll concentration is about 40. And if you look down below, even just our perception is pretty decent that this probably has pretty clear water, not a lot of productivity, and you can see that the chlorophyll is just about 1. So there's a big range, and I'll say in New Hampshire the range is less than in some of the other states. When you look across New England as a whole, it varies pretty widely, although compared to other regions of the country, generally speaking, our lakes are very low chlorophyll. For New Hampshire, 40 is very high. If you're in Mississippi, that's what you're trying to regulate down to. This is sort of your goal, to get some lakes down to 40 micrograms per liter. So in any case, how do you make this translation between what you or the sensor is seeing to the water quality information you're interested in? And as I said, you have a lot of different colors. One of my favorite lakes, Shelburne Pond, which is in Vermont, is that upper left-hand corner. I mean, sometimes the water is so green you almost think that somebody dumped paint in the water, but really, optically, how do you make sense out of that? Well, there's a series of things that are important differences between remote sensing for land and lakes, and especially if you have a lot of experience with remote sensing for land, sometimes you're not thinking quite along the right lines. Now, first, we've already talked about the fact the intensity of the remote sensing signal for land is very high compared to lakes. So in the brightest lake in the world, about 10% of the light that hits the water is coming back. And you could see from that graph in the beginning that you had this little tiny signal in the lower left-hand corner compared to what comes back from the land. And so because of that, atmospheric correction is really important. So in land, sometimes the images are corrected. It may happen when you're looking at lakes, and I could also say for most of these things, oceans is true as well. The atmospheric correction is really important. You have to remove the effect of the atmosphere from your signal. Otherwise, you don't get to see that small signal coming from the water. And in land, infrared light is very important. And in fact, that image of the land in Durham that I showed previously, it was using some of the infrared bands to display. In lakes, infrared is not as important because most of the time, most of the infrared light is just absorbed by the water. The very near infrared, which we'll look at in a little bit, is important, but a lot of bands that are designed for satellites for studying land just are pretty much useless for lakes. And also, water features, as we'll see, need very discrete bands or little tiny, the ability to measure very fine differences in what's going on in that wavelength range, where land sensors often they're wider. And the approaches are very different. In land, you're looking for variability. In water, you're really looking for how does the chlorophyll interact and what is the bio-optical properties, so how does the actual biology affect the optics in a very different way. Land, there's a lot of classification. Lakes, you're really trying to use optical modeling. And the approach often for some land is that you have, especially in classification, you're doing ground sampling. Because you have different sorts of images, you need to kind of know what's on the ground that day. If you do things well with remote sensing of water, you can figure out the model based on some sampling, and then you can apply it across time to any image you can get your hands on. And that's, of course, where that atmospheric correction can be very important. So there's some pretty big differences when you're looking at remote sensing of land versus lakes. I'll see all of these are very general statements. There could be some difference in each one when you get to specifics, but generally speaking, these are some of the big differences. So very briefly, you have light hitting the lake, bouncing to the satellite, and data is being collected. This is how remote sensing works for almost everything, but the interesting thing is what happens once the light hits the lake. And even when light hits land, when it hits pavement, when it hits trees, there are things that are happening. But in the lake, I think it's a little bit more complex. First thing that happens when sunlight hits the surface of the water is that a lot of it just bounces off right into your face. And if you've ever been on a lake in the summer or the ocean and you look down, most of the time you see the sky or the sun. Now that's the reality of remote sensing of water. Part of the problem is you don't care about that signal at all. In fact, that's noise to you and you have to try to figure out a way to get rid of that. What you're really interested in seeing is once the light goes into the water, what happens? Now, some of the light that comes back out of the water will be due to scattering, either coming directly out or bouncing around and then coming out. So this is also sort of a background signal based on what water does to light. But the most interesting thing to most people is what happens when it hits a particle, especially if this is something like phytoplankton or algae. So several things can happen. One, it can be absorbed. And that, of course, is what phytoplankton, algae are very good at. They're very good at taking and harvesting light. Just like any plant, they have different pigments that capture the light so they can convert it to chemical energy. Also, they will scatter. So some of the light that hits the particle will bounce off, and eventually, if it keeps bouncing, it will go out of the surface. And then also, there's fluorescence, where these phytoplankton absorb the light, and then they actually emit the light in a different wavelength. So really, when you're looking down on the water, you want to take out the reflection from the surface. You aren't going to see the light that's absorbed because it's stuck in the phytoplankton. It never comes back out. And what you're going to see is a light that's either scattered or sometimes a light that's fluoresced. So really, that's what you're trying to do, is make sense out of that whole system. And important, reflectance is just a percentage. What's coming out of the water versus what went into the water. So measuring what's coming down and what's going up is important in the remote sensing of water. So there's this one little math symbol for people that care about this sort of thing, but I kept that to a minimum in this presentation. This is what you really want. For every photon that's hitting the water, what happens to it? Does it come back out? Does it reflect? Does it go in? Does it get scattered? And that's what you're trying to make sense out of. Now, how do you do that? There's a variety of ways you can do it. One way is to go out in boats and try to get out when the satellite is flying over and try to take samples. Now, you can do that, and sometimes that works. One of the biggest problems with, or many of the problems with that, is that clouds can be a big issue. So you can be out there on a day, you have all your sampling done, everybody's geared up, they go out in the water, and then a cloud is over your lake and the moment the satellite flies over, and so you don't get any data. Also, because you're using satellites, you have a problem with atmospheric correction being part of the way that you're developing your approach. So it could be that the atmospheric correction that day didn't work really well. It didn't remove the effects of the atmosphere, and all of a sudden you have noise introduced into your approach. Also, satellites have a variety of sizes of pixels. Some of the satellites that are best for water happen to have big pixels. They're 1 kilometer or half kilometer. So if you take one sample of water in the middle of a kilometer pixel, does that really represent the signal you're getting? And also, different satellites have different bands. So what you'll see in some of these spectra is there's a continuous measurement across all of the wavelengths. Well, satellites don't do that for the most part, and they choose where in that range they're going to measure based on what they're designed to measure. And some of the satellites just simply don't have good bands. So can you use a satellite? You can, but really the best thing to do is make your own high-quality spectral measurements right on the water. So basically have a satellite, on quotes, that you can bring with you to make the same sorts of measurements and deals with all of these issues. So this is really what we're talking about when we're developing the approach. How do you make that translation from what an image might look like to what the actual parameter is that you're interested in, like chlorophyll? And this is the way that NASA, European Space Agency, all of these groups, when they're looking at how do you design algorithms, this is what they're doing. Eventually, when you get this to work well, then you can apply it to satellite imagery or aircraft or UAVs, and then that's when you do that ground calibration. But there's a lot of work that you have to do first to try to see what it is, what is that translation approach. So there's a lot of different types of measurements that you can make. The top two are some that we've done here at UNH. The bottom two are usually used for marine systems, and they're much more expensive. But basically, these are ways to make those measurements right on the water itself. And so the goal is to take this, your color of what you see with your eyes, take this information that you have, and turn it into these nice spectral patterns. And just quick reference, the remote sensing reflectance is here. Sort of the higher this goes, the more intensity of light is coming out of the water at that wavelength. And the wavelengths here go from 400 to 725. 400 is blue, 500-ish is green, 700, 600s are red, and then this is a little bit into that near infrared. And the interesting thing, you can see this lake, which has lots of particles and has lots of phytoplankton, the top level here is 0.035, where you look down here where there's not that much in the water, the top level is 0.0035. So there's a lot less light coming out of this lake than there is coming out of the top lake. So the most important things that most people are interested in are measuring plankton for water quality perspective. And plankton have a pigment called chlorophyll. So this is the absorption of chlorophyll. It has two peaks here around 440. It also has a peak around 675. And if you're interested in cyanobacteria, cyanobacteria have their own pigment called phycocyanin. They also have chlorophyll. But almost no other organisms that you'll find in a lake has phycocyanin. So a lot of people use that as a marker to try to find cyanobacteria. So really, from a phytoplankton perspective, these are the things you're most interested in. You have these big absorption peaks of chlorophyll at these different wavelengths, and you also have this absorption for phycocyanin for cyanobacteria. Now, of course, the interesting thing is since these organisms are absorbing the light at these wavelengths, you're not going to see the light at these wavelengths because the organisms are trapping it. So really in the signal, instead of looking for peaks here, the signal you're seeing is reflectance, so what's coming back out of the water. Really, you're sort of looking for valleys. So if you see a valley at these wavelengths, or the deeper the valley is in your signal, the more of that stuff is in the water absorbing. So when you try to look at, well, what is coming out of the water, and these are two typical spectra, maybe of a lower chlorophyll lake around 6 and a higher around 36, you can see these dips and weaves that we were talking about here. And the main points to look at are these bands. You have chlorophyll on the left, and over here you have a lot of scattering that happens in the water for a variety of reasons, so I'm not going to go into at these wavelengths. And then you have the effect of water sort of taking away that infrared here, and you have phycocyanin, or the cyanobacterial pigment, absorbing here. So these are the features to look at to understand when you get your signal. Now, you have your nice clean signal coming off of your equipment. You can also pretend to be any satellite you want by saying, instead of seeing the clear signal, what if we were this satellite or that satellite? What would we see instead? And this is an example of looking at a satellite platform called Maris. It shows you all of the different bands. So instead of getting a smooth curve, you would get bands at those different lengths. And then there's a whole bunch of different ways that you can look at comparing one peak to another peak to a valley. There's a wide variety of approaches that you can use that we're not going to get into specifics today. So how do you translate that into your map? One of the things that I did for my dissertation was go around to a lot of lakes in New England. I didn't go to all of these myself, but I went to at least half of them, and make measurements of the reflectance of these lakes, and also have measurements relating to water quality characteristics. So some of these have cyanobacterial toxins. All of them had chlorophyll, Secchi disc, to try to get an understanding of what is all the diversity in lakes. What is the total amount of variability in this reflectance, and how can we come up with a method that works for New England lakes in general to predict chlorophyll, to estimate chlorophyll. So if we had a satellite, it flew over, what algorithm could we apply to it to get a good estimate of chlorophyll? Well, I looked at it from the perspective of the best case scenario, which is this nice little smooth curve, and then also from the perspective of what if I was X satellite? What if I was Y satellite? What if I was MODIS? What would that look like? What are the best approaches? So this was what they often call spaghetti plot, which shows all of the spectra, and it gives you a good idea of where the variability is. Down here, not so much variability. It didn't matter if the lake was 1 microgram per liter or 120. But there's a lot of variability here, which we would expect, those scattering peaks, and also you can see the chlorophyll absorption here and the phycocyanin absorption here. There's some variability. So in the hyperspectral, we're not going to get into this too much other than to say, yes, there were various techniques for the hyperspectral. So using all of the information, trying to optimize, if I had all of this, which I do, what's the best approach? And I had dozens and dozens of options that I tried. I will say that if you look at this graph, below root mean square of about 0.3 are techniques that work fairly well. So you can see that even though I'm not going to explain what all of these mean, that there were a whole bunch of approaches that could work for remote sensing in New England lakes, and a lot of them were very similar. So there wasn't a few that worked extremely well and a whole bunch that didn't work at all. So this was both reassuring in some ways and also a bit frustrating because there weren't some that came out really highly compared to others. but it shows that there's a whole bunch of different approaches that could work for translating remotely sensed imagery to water quality, to chlorophyll, if you had all of the bands. If you didn't have all of the bands, I tried a whole bunch of different satellite platforms. One of them, just to show you, was MODIS. What you can see is there's a little more scatter around these lines, but you have down here what the, I'm sorry, I should have done this on the other slide. You have down here what the remote sensing signal is versus measured chlorophyll, and then you use this to see how well can you predict chlorophyll versus measured. So this shows you the relationship, and this shows you how well that relationship works. You can see there is a way that works. There's more scatter. This is a satellite that's designed for studying ocean chlorophyll, so it doesn't work quite as well in lakes, but it still did work. And there was a variety. You can see they're closer to that 0.3 threshold than they were for the hyperspectral, but there are some that clearly do work for New England lakes. So this is a success to say, yes, doing all this careful measurement, all this study, there are ways that we can translate. Then, towards the end of my dissertation, I started to come to grips with the fact that while these represented New England, does this lake here in New York count? Should it count? Of course. Maybe. What about these lakes? These are both in New England. Do these represent similar areas of the world? In a way, because of the boundaries we've drawn, they do, but in another way, those are very radically different areas of the world. So a lot of the remote sensing research has been looking at what is the best algorithm for New England? What is the best algorithm for the open ocean? What is the best algorithm for the Midwest? And I started to think about, well, how can we come up with algorithms that will work no matter what, and we're not going to have to say, yes, this is open ocean, yes, this is New England, yes, this is Maine, but instead have the algorithm start to figure out by itself what's the best approach to use. So one of the things that I did was look at my data from my dissertation, plus the other part of my dissertation, which was several trips I had taken to the Great Salt Lake to collect data. And I teamed up with one of my remote sensing friends from Spain, whose job it was to do a lot of sampling of lakes all over Spain. And then I connected with some of the ocean remote sensing people here at UNH, and they gathered from NASA's database about 169 different spectra from coastal regions. So we compiled this list of almost 500 spectra from lake, coastal, and marine waters from around the world, and said, using this giant data set, can we come up with a good way to translate that we can use anywhere, maybe not in the open ocean, but anywhere close to land or in lakes? And so one of the things that we tried to do was look at the fact that, well, you know, one algorithm's probably not going to work everywhere. And the idea that you're going to be able to say only this one in New England, it could be that within New England, there are different regions or different approaches might make sense. So one of the things we did was group all of the spectra that we had all in one place, and then let this clustering algorithm say, how many different types of spectra are here? And based on the settings that we chose, we found that there really were 7 different types of water, for example. We call them optical water types. So 7 different types of water. Now keep in mind that this could mean that one lake right next to another lake in the same town could have different types, or even within a single lake, different areas of the lake could have different types. These don't really care where the lakes are located. They're just looking at spectral characteristics of the lake. So you have these 7 different groups or types of water. And then if you look at sort of their average spectra, they look like this. So the approach that this takes, instead of the approach I was using, which is let's fit one type through every single lake we have in New England, is let's look and say each lake, each spectra even, each pixel of an image could belong to one of these groups, or could belong 30% to one group and 70% to another group. So this gave the ability for this approach, this method, to choose as it's going along for each individual pixel what type of water it belongs to, and then use an algorithm that works best for that type of water. Now you're still going to argue about which algorithm might work best for optical water type 7 versus 6 versus 5, but you're not going to say this works for New England, this works for New York, this works for Pennsylvania. So the old approach would have been, all right, we're going to use this Maris algorithm, this satellite platform. It's going to just apply the same algorithm to all of them. You could use something like OC4, which is an ocean color algorithm for MODIS. Okay, the old way, hey, all of the pixels, all of the lakes, all the areas are going to get the same. Or you could let the algorithm say, all right, which one works best for each? Maybe these 3 might be suitable for Maris, these 4 suitable for this other algorithm, and that really results in something called a blended product. So this really lets the algorithm itself pick which one works best and then apply it. So did this work? Did it make sense? Did it improve the scatter of our points? This shows for all of the 500 lakes or spectra in that, here is your actual chlorophyll versus the modeled chlorophyll for ocean color 4 algorithm. Here it is for Maris. And if you care, these little colors are based on the optical water types. And then this is what the blended product looks like. So by letting the individual spectra be classified as belonging to different groups and then letting different algorithms be applied to them, it basically took the best of both algorithms and produced a more accurate estimate of chlorophyll. And the beauty of this is that it just happens once you have that classification set up, the actual you don't have to worry about, does a lake fit into a certain category? The algorithm will choose which category that water fits into. So once you set it up, it does this itself on a pixel by pixel basis. So what did that do? Did it make it more accurate when you looked at things like root mean square? It did. It got it down close to that 0.3. And keep in mind, this is an approach that worked across a wide range of countries and a lot of coastal areas. It took down the absolute error down to 40%, which for remote sensing of water, once you get to 40 or 35, it's pretty hard to get any lower than that. And most interestingly, the bias got removed and went to almost 0. So this shows you, was the algorithm more likely to err on the side of being positive or negative? And you can see that each of those individual algorithms had their own leaning, but that blended algorithm really allowed the bias to be almost nothing. So it was as equally likely to overestimate as it was to underestimate. So this approach, which is relatively new, seems to really be the best of all worlds. It lets the water pixels choose, different lakes choose what sort of group they belong to, and then it is better than any single algorithm alone at handling a whole bunch of different types of water. So that would mean that if you were looking at a lake, you might have what the OC4 version of the chlorophyll was for a given image. You could have the Maris version for a given image, and each of those pixels would say what percentage they belong to this, which percentage they belong to that. You would apply the maps that each of those algorithms would have produced by themselves. And then in the end, you would get this blended final image, which would give you the best, basically, of both of the algorithms and hopefully avoid some of the pitfalls of each. So this is a lot of information. This is a relatively recent paper. It is, I would say, very technical in that there's a lot of math. I actually skipped quite a bit of the math and the equations that's in it, but this is one of the most recent approaches. This was published, well, available in January. I think it was actually printed maybe in February. But this seems to be one of the ways that we might get past this problem of having to do as much direct research on figure out an individual lake or an individual region what works best. Since this took so many regions into account, now the next step, of course, is really trying this to see how well does it work. Trying to get aircraft flights, satellite flights, and then do that on-lake monitoring to see, does this work or where does it fall down? Because when push comes to shove, all remote sensing use and looking at water quality, it's only estimates of what's in the water. And you do have to do that validation to make sure that the estimates work. However, if those estimates are accurate, you don't have to do validation every day. And in fact, you can only periodically check. Can this be applied to satellites? It can be. It can model any satellite because it was designed on hyperspectral data. So this would work with any satellite platform. Can it be used for UAVs? Sure, it could, as long as the UAVs actually have the correct spectral information, which is part of the struggle, but you could. Aircraft over flights, certainly. And even those devices that you carry around the lake, those you could very easily use if they're mounted to a boat and you could just drive around and collect data. While that may not be remote sensing in some ways, because it's not what we think of as remote sensing from aerial aircraft, using that same relationship between what the spectra look like and what it means for the water, you could set up one of those on a boat with a GPS unit and just drive around the lake quickly and get a map based on this same approach. So we think that there's a lot of potential for it. There's a lot of variability. It builds on something that both Tim Moore and Mark Dow had worked on for oceans in the past, this same sort of blending approach, but it's the first time that that's been done for lakes and coastal areas, which are the trickiest for measuring water quality because they have these problems with the stuff running off from the land that the open ocean doesn't have. So this is a very quick fly-through of some basics of remote sensing of water, looking at spectra, figuring out what parts of them may be interesting, looking at some differences between land and water, and then thinking about the research that's been happening locally about how do you take whatever image you have, whatever satellite you have, and how do you translate that to a map of water quality that could work, at least in this region, and then recently we're trying to move out past just New England. Now the application of this will depend on a lot of things. It'll depend on what satellite platforms are available. It'll depend on what happens with UAV, what types of overflights we can get. A lot of that still has to be determined, but at least now this is a really solid approach to be able to test a lot of these things in the real world. There's lots of other papers that have come out, lots of other uses of remote sensing, and if we do have a follow-up, I chose this one to focus on because obviously I was involved with it directly, but it also represents one of the most interesting things that have come out recently. In a follow-up webinar, if people want to know more specific uses and have me focus more on different papers and different applications that have come up recently, I'd be happy to do so. But considering the timing, I think this is about as long as I wanted to go with this first webinar. All right. Leslie, any questions?
Yes, there are a couple of questions. Let me just open this up so I can see them better. So the first one had to do with the term hyperspectral.
Yes.
How many bands were you talking about?
I'm trying to think. I mean, there's also the idea of ultraspectral. Hyperspectral can mean multiple bands, probably, well, I would say multiple contiguous bands. So you can see a lot of satellite platforms will have maybe 7 or 8. Some of them even have 20 bands, but they're not contiguous, meaning that there's gaps between where they measure.
Mm-hmm.
For hyperspectral, they're always contiguous. There's no gaps between them. I think you're talking could be 30, 40, 50. On my radiometer, I measured every 0.3 nanometers, so there were hundreds of bands. But from a satellite platform, from the bandwidth and also the sensitivity of each band, the smaller the band is, the less total photons hit it for the same image. There is sort of these theoretical limits, and also how useful would you want them to be, or how useful is it to know every 0.3 nanometers. A lot of things I've seen, people usually say 2 or 3 or 5 is enough. So if you take 5 and divide it by 300, that could give you approximately how much you would need to cover the visible spectrum. Mm-hmm. But yeah, there's ideas of ultra spectral but hyperspectral many, so I'd say 50, 60-ish, but that's just an estimate, and they would be contiguous, so there's no gaps between them.
Okay. The next question is, how were training and validation data separated?
Yeah, that's funny, because the interesting thing about my work is that I am a person who's, from this perspective of my life, my background was limnology, and remote sensing was something that I learned for my dissertation. And in everything that I did, I always had validation data. I had experimental and validation data. And 2 of the people on my committee were from the Ocean Remote Sensing group here at UNH. And one of them used to work at NASA. In fact, she designed some of the satellite sensors that I was simulating for my research. And they both poo-pooed the idea completely of doing experimental and validation data, because they said that they thought that that wasn't true validation data, because it was just one big pool of data that I mashed into 2 separate groups, and that I was only really testing my own stuff, and hooray, it worked. So they wanted to have some sort of validation that was completely external to everything I had done in order to be true validation. So they said, don't bother splitting your data set. Put it all together into one single data set, make your best estimate, your best algorithm based on that, and then if you truly want to validate your data, get it from somewhere else. Have this completely separate. So I wasn't going to use that approach. That's not the approach I'm used to. I'm used to breaking it into two sections, but they felt, and one of them, the woman who worked in NASA had a very strong statistical background too, and she basically told me, don't do that. For what you're doing, use it all as one, come up with your best estimate. Anything else you do, she basically wouldn't accept. And so when you're on a dissertation committee, the people on your committee have a strong influence. And the good thing is that since I've moved outside of the data I've collected and started to bring in these other data sets, I've had an opportunity to look at and see if those relationships work, which was one of the reasons I was excited about collaborating for that paper. But that was my initial approach, which was rejected by my committee.
Okay. I don't know if I should read the response to that from the guy who asked that question.
Go for it.
Were you able to test relationships between the 7 different reflectance classes and other lake characteristics such as depth, velocity, and wind speed?
Well, yeah, we did look at, in the paper it actually has tables of sort of I think it's the low, the mean, and the high of a variety of different components. So for each optical water type, we know that the average chlorophyll was this, or the average water quality or clarity was this. Or there were definitely in the paper, it showed different groupings. Now, of course, there's overlap. That it's not only lakes that are 2 micrograms to 5 micrograms split into optical water type 2, and only 5 to 10 fit into optical water type 3. But yeah, all of those spectra had those characteristics. The limnological data for it, so in the paper it does show those. We haven't done a lot with the analysis of those to try to come to grips more of why the spectra were the way they were or what it meant specifically, but that's something that we hope to do in the future. But like the wind, the depth, for example, what were the 3 things that he said?
Depth, velocity, and wind speed.
Well, velocity and wind speed wouldn't matter at all in these because I don't know in a lake what a velocity would be. But in wind speed, because these were, yeah, they were remote sensing reflectance, so any effect of wind on the surface of the water would have been removed. And depth, all of these were done in optically deep waters, which means that the bottom had virtually no or no effect on the signal at all. But the depth of each lake is known. I don't know if we included that in the paper or not, but we have the depth information for all the lakes. Yeah, to me, that paper was just the beginning, the first attempt to assemble all this, but there's lots of questions left. Including
Okay. There's a question and maybe a follow-up from another person here. And you may have already addressed this in some of the things you've said so far, but I'm going to read it anyway. Did you use ground truthing, and then he puts in parentheses water, because obviously it's not ground truthing, water truthing, samples to verify the accuracy of the image classified with the blended index?
Yes, the answer to that, for that paper, the answer is no. There's a certain amount of things that could fit into that paper, and actually going that extra step was not one of them. This was just showing for a given image, looking at variability, looking at characteristics. And in fact, in the paper, what Tim did was look at every image that's ever been collected for that lake and try to see what sort of optical characteristics were there. Obviously, the next step is to actually take some of the lake data that has been collected in the past and see how well it worked. But within the context of the paper, there was only so much that we could do. Also in the paper, the imagery was analyzed for a coastal area as well. So there was some response to what the actual reviewer said, but there's only so much you can fit into one paper. But that's obviously the next logical step.
Mm-hmm. And the next 2 questions are related to one another. So one is, it seems like there's a high potential for the use of remote sensing in water quality monitoring.
Yeah.
In your research, did you encounter anything relating to stream systems and specifically sediment loading? And then the next question was just, can this be used in streams and rivers?
Yeah, I mean, the idea that you could look at turbidity or loading from remote sensing, you definitely can. Again, how well it works is based on how much you know about the system and how well your model has been developed. one of the big problems with streams, I think, would be that really if you can see the bottom, I mean, just standing over the stream, if you can look down and see the bottom, then it's very difficult to do any sort of optical remote sensing because the signal from the bottom is so strong that it sort of washes out a lot of the signal from the water itself. So I guess that would be what I would say. These are all techniques for, as again, optically deep water, so you can't see the bottom. The real definition is more complex than that, but we'll go with that, just optically deep. The reality is that sediments have been shown using remote sensing. The question would be how often can you get measurements to make it worthwhile, and also what about the sediments are you interested in? The total amount, their distribution. I think it definitely could be used. All of the issues with using this in an operational way relate to how often you can get imagery or measurements, and whether or not the imagery and measurements you can get have both the spacer resolution, so the small enough pixels, and have the right spectra to get you a good map. But given that if you had a remote sensing platform that gave you measurements often enough, had small enough pixels, and had this right bands, you could do it. That's always the big caveat. So there is definitely research along that lines. But anything you can see the bottom of in water, it's not impossible, but it gets very tricky.
Okay. Okay, that's all I have for questions. If anyone has any other questions, feel free to send them in now. And so do you want people to also comment if they're interested in another follow-up webinar on a similar or topic or extension of this topic?
Sure. They can either do it right in this, or you feel free to get in touch with Leslie or myself with any ideas you have.
Yep.
This was sort of an overview and some of the research that I've been involved with in this region of the country, but there's lots and lots of things with remote sensing of lakes I didn't touch on. For example, what are the AV satellite sensors that would work best, and what could they be used for? Or what are different sorts of research topics? What are they looking at in addition to chlorophyll? And sediments are one example where, especially in rivers, that could be something of very high interest. So I think there's lots of topics which could be potentially of interest, but within a half an hour, there's only so much that you can cover. So either comment on this in the questions, or feel free to get in touch with me or Leslie if you have any other ideas about things that would be worthwhile.
Okay. And there definitely were a couple people who spoke up to say they'd like to see a follow-up webinar. And then there is another question. Has this been used on watershed planning, such as Champlain or Winnipesaukee and subwatersheds?
When I first was doing my PhD, there was a graduate student in UVM who was developing algorithms for Lake Champlain. And I know that some work has been done with this since. I have to admit that I haven't followed up as much, and one of the things I hope to do this summer, especially since this paper and this research was released, is to go follow up with people in the region and try to see what it is exactly that they're doing. I know some work has been done. What exactly has been done with it, I'm not sure, but obviously Lake Champlain, because of its size and the fact that most of the sensors that are good for this have relatively big pixels, Lake Champlain would be one of the prime targets for this sort of thing in this region of the country. Other lakes could work, but Champlain is the biggest lake. Keeping in mind that all you need is a little tiny corner of land inside of a pixel for it to be useless for water, because the signal for land is so strong that it washes out the water. So even within Lake Champlain, there are places where it may be difficult depending on which satellite sensor you're trying to use. But there are new satellites come out all the time, or if you had aircraft or UAVs, some of those issues would go away.
And there's another question. Which satellite sensors were used, and which satellites were used in the what satellite sensors are used, and which satellites are used in the paper, in your paper?
The satellite sensors that were, your voice got all weird in the beginning. The question is what satellite sensors were used in the paper?
Which sensors are used, I think maybe for this type of collection, and then also which satellites were used in the paper.
Yeah, in the paper, satellite data was used from the MODIS sensor, which is on, there's two different satellites that it's on. Usually it's referred to as MODIS, but it's Aqua and Terra are the two satellites. And then it was Maris, the sensor, which was on NVSat-1 before they lost contact with it. A few years ago, they stopped receiving data from it. So it was the Maris sensor and the MODIS sensor on those satellites. Those were the data that were used. Now for lakes, big lakes, MODIS is still pretty widely used because MODIS has big pixels, 1 kilometer pixels. So for small lakes, it doesn't work, but it flies over the same part on the Earth once a day. Actually, I think twice a day, but once at night. And it's used pretty widely for big lakes. For smaller lakes, that's still up in the air. Landsat exists, but there's a lot of limitations of what Landsat can do just based on how often it flies over, what its radiometric ranges, or spectral issues. There are new satellites that are being launched or coming online in the next few years which may be much better at this. Maris was the best one for a while until they lost contact with it because it has the right bands and it had 300-meter pixels, which are still big for a lot of lakes, but 300-meter versus 1 kilometer opens up a lot more lakes to it. I would say right now there's no ideal satellite platform for doing most lakes in the world because they're too small for the satellite sensors that work well. But yeah, the European Space Agency is launching Sentinel. There's also on the drawing board plans for a NASA hyperspectral satellite. So there are things that are coming out in the near-ish future or are recently launched that may be used more widely for this. But say right now, Landsat, because it's available, and there are some things you can do with it, although there are limitations. Maris was, and MODIS for big lakes and for the ocean is really what most people use.
Okay. Okay, that's all I've got. I'll say again, this is your last chance. Send in a question. Oh, no, that's just a thank you. You've gotten a couple of thank yous, just so you know.
Okay, great.
Very interesting, I think. All right, I think we're done, unless you have anything else you want to share.
No, I would just say thank you, everyone, for joining. I know that this is a different sort of webinar than most of the topics you've probably heard from me and most of the topics that come through VCGI, but I was glad to see that there are people interested, and don't hesitate to get in touch with me directly using this contact info here if you have any other questions.
Great. And thank you very much, Shane, for giving us a new and interesting topic.
All right. Thanks, Leslie, again for hosting this and coordinating this, and thanks to New Hampshire Space Grant for supporting it.
Yes, our pleasure. All right, everybody, have a good day, and remember this has been recorded and it'll be posted on the VCGI YouTube page. Thanks.